Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be discussing the concept of work in a physics sense. So what is work and how do we determine it? And in future videos, maybe what does it do for us? Or what can we do with it? Okay, so at this point, if you're going in order of the intended order of these videos, you will have at least made it through most of the videos on forces and on kinematics. So today's video, we're introducing work, and you need to know what force is because the way that work is defined involves force and it involves displacement. Now, we typically represent work with a capital W. The way that we define it is that work is force dotted with displacement. So F dot, and then your choice of what you want to use for displacement. I'm going to use a D. So a few things have happened here. I've got a vector, I've got another vector, I'm multiplying the two together. We need to sort of break that apart and figure out what it means. But before we do, it's also worth noting what are the units for work. So the SI unit for work is the joule. So joules are represented by a capital J. And the way that you get a joule is that 1 joule is equivalent to 1 Newton times 1 meter. So 1 Newton of force times 1 meter of displacement. Okay, back to this equation. So dot product here. So let's note that this is a dot product. The way that dot products work, as you'll recall from watching the vector videos, is they sort of like project one vector onto another, or they kind of look at how closely do two vectors align with each other. So if I have two vectors that are like this, for example, I'm going to get a different dot product than if the two vectors are, say, like this. These vectors represent the same length in both cases, same magnitude for each, but the angle between them is somewhat different. And that in turn is going to give me a different answer than if I have, let's draw one just slanting off like this, for example, something more like this. Okay, these will all, even though the vectors have the same magnitude in all cases, they will all give me a different answer for this dot product. So how do we compute dot products? Well, there's a couple ways of looking at it. One is that you could say work is therefore equal to force in the x direction times delta x plus force in the y direction times delta y plus force in the z direction times delta z, all as applicable, of course. Okay, so this is one way of doing a dot product. This is sort of the Cartesian approach. So that works. You will get a correct answer here. This is incidentally a single scalar number that you will get at the end. Basically, even though you have two vectors to start with, you'll end up with a scalar. That's true regardless. So maybe we should note that this is a scalar, even though these two are both vectors. The way that it becomes a scalar in the Cartesian approach is that you have first component of force, first component of displacement, and you multiply them together. You have first component, second component of force, second component of displacement, you multiply them together. Third component of force, third component of displacement, you multiply them together. And then you add those three products together. So you end up with one single number at the end. Okay. The other way that you could go about getting work or dot product in general is to take essentially the magnitude of each one of these vectors. So F and D, and then multiply those two magnitudes by the cosine of whatever angle is between the two of them. And that angle could be in 3 dimensions or 2. We might call this the polar approach, even though it can also be in 3 dimensions. This one sort of requires an additional picture. Really, any of these pictures will do, but I'm going to draw it down here just so that we associate this latter equation with this diagram. So let's say that I am applying a force on an object, and as a result the object has a displacement d, shown here and here. The dot product between the two of them is the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between those two vectors. And maybe I should put a little side note that as a reminder that we are using f without a vector over it to represent magnitude of the vector f, and we're using d without a vector over it to represent the magnitude of the vector d. So that's our little note well note. Okay, so that's how we go about calculating work, and in both cases we're kind of in some sense done. We have work. It will be a future video before we discuss what we do with work, but it might be worth considering some basic examples here to make this point complete. And before I do the basic examples, it's also maybe worth noting that each individual force within a system can do work on the object. We usually ultimately care about the total work done on the object by all the forces together. So in that sense, we could say that the total work done would be the total force, meaning the sum of forces, dotted with the total displacement. Okay, so now some conceptual examples. Let's say I have an object which is sitting on the ground like this, and let's say that the object is lifted up into the air by some total height. So this is some height. How much work will gravity have done on the object? Well, we know that gravity in the entire lifting portion of this, gravity is in this direction. It's constant, it's mg downward. So our work done by gravity should look like m times g dotted with h. And what that actually ends up looking like is negative m times g times h. Now you may be wondering, where does the negative come from? And the answer is because if I were to draw again the gravity or the force vector, this is my force, which is m times g, it's downward, and my displacement vector, it started low and ended up high, would be like this. So what is the angle between these two vectors? The answer is theta is 180 degrees. So if I take the cosine of 180 degrees, I get -1. So a reminder, cosine 180 degrees, make sure your calculator is in degree mode if you're double checking this, but cosine of 180 degrees is -1. So when I do m times g times h times cosine theta, I get mgh times -1, which is negative mgh. On the other hand, if my object starts up here and is released and falls to the ground, now, so this is, we could say, lifting against gravity. If I let it fall with gravity, then I have a slightly different case. Fall with gravity means now the object falls this far, h, and gravity the entire time is also straight downwards. So let's try to make it a little bit better of a parallel there. So m times g. In this case, where it is falling, we could say with gravity, or under the influence of gravity, or in free fall, whatever you want to call this. In this case, my work is again m times g dot h, but this time the work is mgh. The work done by gravity is positive, because over here I have theta equals 0 degrees, and I know that the cosine of 0 degrees is actually positive 1. Okay, so if we're going in the same direction as the force, or if we're going in the exact opposite direction of the force, that changes whether the force is doing work on the object or against the object, with the motion, against the object, against the motion. Okay, so that's kind of like example conceptual number 1. Now let's consider another conceptual example. Let's say that I am carrying an object. So here's the object that's being carried. This object has mass m. Gravity is acting downward like this, m times g, and I am carrying the object over to here. I am also a stick figure, apparently. All right, and again over here, mg is downward. What is the direction of the displacement? Well, basically our object started here and ended up right over here. My displacement delta x, in other words, is to the right. So if I draw this sort of diagram that shows displacement, or d, on it, and I draw the gravity, it's like this, m times g, these two are perpendicular to each other. So this time, if I go work is mg dot d, I get m times g times d times cosine of 90 degrees. This is 90 degrees. And the cosine of 90 degrees is 0. So the work done by gravity in this case is 0 joules. There's no work being done by gravity. There may or may not be work being done by me, but gravity has done a net amount of work 0 on this box. Incidentally, the net amount of work done if I have a closed loop with gravity is also 0. I will have worked, let's say I pick the box up, carry it across the room, put the box down, and then somebody else slides it back to where it started from. Well, I will have done this much work in picking it, or gravity will have done this much work when I picked it up. Gravity will have done this much work when I put it down. Add those two together, I have 0. Moving it across the room, I did 0. Sliding it back across the room, gravity again did 0. So the total amount is 0. You can add them up, you get 0. Closed loops within, or closed loop paths within what we call conservative forces do 0 net work. And so gravity is what's called a conservative force. An example of a non-conservative force, for what it's worth, would be something like friction. If I do a closed path against friction, or against friction and air resistance, something like that, a net amount of work will have been done. Let's do one more example with maybe some numbers. Actually, before we go to one more example with some numbers, let's look again at this in Cartesian. So in Cartesian, what we would have is work is equal to f sub x delta x plus f sub y delta y. And there is no fz or delta z here, so we only need these two terms. But we could say fz delta z, both of which are 0 here. Okay, well, this term right here equals 0. There's no x component to gravity which is oriented only vertically. Gravity is vertical. The delta y term also equals 0. Box moved horizontally. And that means that both of these terms must be 0. So my work in this case is 0 plus 0 plus 0 equals 0. So in the Cartesian case, I again get 0 work done. Okay, now like I said, we'll do an example with maybe some numbers. All right, in the example that we have, we ask how much total work is done sliding a box horizontally along a frictionless surface if the applied force from the person pushing the box is 160 newtons at 15 degrees below horizontal, assuming that the box has moved a total distance of 5 meters. As always, it's a good idea to draw a diagram here to help us solve the problem. So here's my box. I'm going to move it a total displacement d of 5.0 meters. So from one location to the other. I have a person pushing on the box like so. And that pushing force is basically like this. So this is 160 newtons worth, and we're told this is at 15 degrees below horizontal. So this is 15 degrees. Now there are two other forces present here, but neither one of them is doing any actual work on the system. We have gravity, m times g. We have the normal force, Fn. Those two are not doing any work, again for the same reason as no work was done by gravity in this case. Both of them are perpendicular to d. This also is perpendicular to d. That means that when you do the dot product for this one and or for this one with d, you get 0. Okay, so what's left is work, we could say, is Fg dotted with d, that is 0, plus Fn dotted with d, that is 0, plus whatever push force, we could label this thing here as like F push or something like that. So plus F push dotted with d. All right, so what is F push dotted with d? Well, that would be the push force, the distance, and then the cosine of the angle between the two of them. So that is 160 newtons, 5 meters, and the cosine is of 15 degrees. So we would put all that into our calculators to get 772.74 joules. So if we're keeping two significant figures, that would be 770 joules roughly worth of work that has been done on this box. Now, how in the world are we walking to push this box along this frictionless floor? That's a mystery that I am not here to answer. Maybe the box is narrow and on a frictionless stretch, and the man has a wide stance on a friction surface. Maybe there's a walkway that's raised up a little bit and he's pushing the box somehow like that. That's neither here nor there. In any case, about 770 joules, 772.740661 joules, 2 sig figs, 770 joules of work has been done on this box. And that's all for today's video. Hopefully you've learned a little bit about work, and thanks for watching.